This lesson is on electric potential energy. And as we shall see later on, this will be necessary for us to be able to discuss currents in electrical circuits. What we aim to learn about electric potential energy is how to understand concepts in electrostatics in terms of potential energy in addition to in terms of electric field and electric force, how to calculate the work done by the electric field when we have a change in electric potential energy, or when we have a change in a charge configuration. And we would also like to differentiate between work done by the electric field and work done by an external force against the electric field. So we know that the electric field exerts a force on charged objects. So therefore, if we're to move a charged object in an electric field, we need to do work because of this electric force. The electric force itself is a conservative force, like the gravitational force. This means that if we're to move a charge in an electric field, the work required to do that is not dependent on the path that we use to move this charge. So let's take a look at the expressions for work in an electric field and how we can calculate. So in general, if we have any kind of force, we know that the work done by this force is the force times the distance. And both the force and the displacement are vectors. And if they're along the same direction, we can just express these of the magnitudes of force and distance multiplied by the cosine of the angle that these two subtend. That is, if the motion is along a constant direction, not necessarily the force and the motion are in the same direction. So in general, the force and the motion will be in different directions, but the amount of work done by the force to move the object from here to here is the force times the cosine subtended with the direction of the motion times the distance moved. If we're dealing with an electric force, then our expression for F will be Q times E, the charge times the magnitude of the electric field. And we have very much the same expression now where F, the vector F for the force is Q times E. Now, if the force varies with position along the path, or if the path itself is not a straight line, then we have a somewhat more complex expression. So we then have to calculate the amount of work done by integrating the dot product of the force and the path of motion. So say we have this kind of example, we have this kind of electric field coming from a point charge here, and we're moving a charged object from point A to point B. If we take this kind of path, then at each point we have to take the dot product of the force and the path increment and to integrate these over the entire path to get the amount of work done. So again, we're dealing with the electric field, so then we can express F in terms of Q naught times E, where Q naught is the size of the charge that we're moving. So the integral that we're taking again is along this path from A to B. And this kind of integral that has a general path we call a line integral. Now, as I mentioned already, because the electric force is a conservative force, the work done by it in moving a charge in an electric field in the absence of other external forces is actually independent of the path that we take to do so. So whether we take this curved path or this curved path or this curved path, the total amount of work done by the electric force is the same. And it's in fact also equal to the difference in the electric potential energy between the final and the initial points. So UA here is the electric potential energy at point A, and UB is the electric potential energy at point B. The amount of work done by the electric field is the negative of the difference of the electric potential energy between point B and point A. And that's what this statement here summarizes. So let's now look at an example that we can analyze more easily. Let's take a look at these 2-point charges. So we have a charge at the origin and a charge Q0. And we're moving charge Q0 from point A to point B along this straight line path. The question is how much work is done by the electric force, by the electric field of the charge at the origin, charge Q, in moving charge Q0 from A to B. And because we can choose any path in principle, we choose the path that's most convenient for us, and that's a path along the direction of the electric force and the electric field. So we choose a path along the radial direction from the point charge Q. So in this case, the displacement vector S is going to be parallel to the electric field vector E, and their dot product is just going to be equal to the product of their magnitudes. So let's go through the steps. The work done by the electric field then is going to be Q0, which is the magnitude of the charge that we're displacing, moved from A to B, and we have a dot product of the electric field and the displacement vector, and Q0 times the electric field is just the electric force. So then, because E and ds in our chosen path are along the same line, their dot product equals just their actual product, and ds here is the same as the change in radial direction, radial displacement, so ds is the same as dr. And for E, we use the electric field of a point charge, Q, so E is going to be kq over r squared. So now this is an easy integral. We have 1 over r squared dependence, so we have to integrate by dr from point A to point B. So we'll take out the factors that do not depend on distance in front of the integral. So now we have kq0 in front of the integral, and we just have dr over r squared under the integral. So now we go from A to B. The integral of 1 over r squared is minus 1 over r, evaluated from A to B. So then we have minus kq0, 1 over r between A and B. So this is going to be minus kq0 over rb, this is the final distance, minus kq0 over ra, the initial distance. So then to summarize, the work done by the electric field of charge Q is the negative of the difference of the potential energy in the final configuration and the potential energy in the initial configuration. And that's what this shows. UB here is the potential energy in the final configuration, and UA is the potential energy in the initial configuration. So then we can see that the potential energy of a system of 2-point charges, Q and Q0, that are separated by some distance r, is given just by this expression. So the potential energy of a system of 2 charges, Q and Q0, separated by distance r, is just kQQ0 over r. And this will be a concept that will facilitate our estimate of work done, say, in an electrical circuit. So let's take an example. We have a charge of 7 times 10 to the minus 7 coulombs at the origin, and another charge of 3 microcoulombs. That's now embedded in a raisin that has a mass of 0.3 grams. The raisin is then brought from very far away to a point that's only 20 centimeters from this charge at the origin. And the question is, what is the electric potential energy of the final configuration? So the thing is that we are only concerned here with the electric potential energy, so in fact the mass of the raisin matters not. So then we just use the expression for the electric potential energy that we came up with in the previous slide. So here's our solution. The electric potential energy is K, Q1, Q2, each of these 2 charges divided by their distance. So we have K here, we have Q1, we have Q2, we have the final distance, and this is our final electric potential energy of the system. A couple of things of note here. This unit is Newton meter, but we're talking about energy, so it really should be joules, and indeed, we know that the product of a Newton meter is a joule, as we know for energy. And we also, as I already pointed out, because we're talking about the electric potential energy, this is actually independent of the individual masses. So let's revisit this part where the work done by the electric field really depends only on the change in distance. It does not depend on the path. So if we wanted to move charge Q naught from, say, point A here to point B, and we're in the field of charge Q, what matters really is only the change in distance between RA and RB, and the actual path will not matter. And we can choose the simplest possible path if we wanted to integrate the amount of work that is done. So if we were to separate this path in two segments, one a radial segment, which we can easily integrate because here the displacement vector and the electric field vector are parallel, so the dot product is just the product of the magnitudes. And then we can add a second component of the path that is azimuthal, so always perpendicular to the direction of the electric force. Then the dot product of the electric force and the displacement vector along this path is always going to be 0 because they're going to be perpendicular to each other. Then we can see the work done along the radial path segment 1 is the same as before. It's a change in distance. And the work done along segment 2 is actually 0 because the dot product there is 0. So, to conclude again, the potential energy depends only on the distance r, and there is no work done unless the distance between two charges changes. So let's recap this concept because it's a very important one. The electric potential energy of a system of two charges is just the product of the charges times k over the distance between them. The electric potential energy is a scalar, not a vector. And because of this, it is actually sometimes easier to just work with the electric potential energy than with the electric force or the electric field, because then we actually have to apply dot products. If the separation between these two charges is infinitely large, then you'll see that the electric potential energy of the system is 0. If the two charges have the same sign, both positive or both negative, then you see that this product is positive, so the electric potential energy is positive. If these two charges have opposite signs, then this product is negative, so then the electric potential energy of this system is negative. So let's take a look a little bit more in detail in the case when we have two charges of the same sign. So we have two positive charges, so we know this is the case where the electric potential energy of the system is positive. And let's now see a fine distinction, but an important one. Let's differentiate between work done by the electric field in changing this charge configuration against or versus work done against the electric field by an external force, say us, if we wanted to move one charge from one position to another. So again, the two charges have the same sign, so they're both positive here. If we're bringing the charges closer together, so the final distance is smaller than the initial one, then, according to this, when R becomes smaller, the electric potential energy decreases, so the electric potential energy of the final configuration is greater. So then the work done by the electric field is, again, minus UR2 minus UR1. And because this is greater than this here is a positive number, with the minus in front is negative. So when the charges are being brought closer together, and the charges are of the same sign, the work done by the electric field is negative. The electric field does negative work in this case. So an external force does work, and the electric field is having work done for it, or against it, I should say. The external force, we, are the ones doing positive work against the electric field to bring these like charges together. So they can be both positive or both negative. Now let's take the opposite example. We still have two like charges, but we're actually now moving them further apart. So now with the final distance greater than the initial one, the final electric potential energy is smaller than the initial one. So then the work done by the electric field, this is work done by the electric field, is again the same expression, minus UR2 minus UR1. Now this is a negative number, and with the minus in front, this becomes positive. So the electric field is doing work when it moves like charges further apart. And this makes sense. The electric force wants to move these charges further apart, so the electric field is doing work in moving these charges further apart. We, as the external force, are doing negative work against the electric field when like charges are moved further apart. So we're not doing any work, we're having work done for us. So the electric field does positive work when the charges move in the direction where the electric field wants them to move, and the external force in this configuration, in this situation, does negative work. The electric field does negative work when the charges are moving against the direction which the electric force wants to configure them, and an external force then is required to do that amount of work. So far we looked at the situation where we had two charges of the same sign, so a system with a positive electric potential energy. Just a quick recap now of what happens if we have the opposite situation, two charges with opposite signs, so a system with a negative electric potential energy. So we have a plus and a minus charge here. So then, when these two charges are being brought closer together, that's what the electric force wants to do, then the electric field is doing positive work. And the external force is doing negative work against the electric field when these charges are being brought closer together. However, if the electric charges are moving further apart, then the electric field is doing negative work because the electric field actually wants to bring them closer together. And it's the external force that's pulling these charges further apart is doing positive work. So these distinctions are important when we have to consider what amount of work is done and whether an external source of energy is needed to change a charge configuration. And I'll revisit, in fact, the example that I already showed you about the electric potential energy of a system of two charges, but now we'll ask a few more detailed questions and I'll work these out in a written solution in a separate video.